Hello everyone, my name is Pengfei and I'm from Tsukada Lab, the University of Tokyo. I'm very glad to be invited to present my research on this year's VTC. And today my presentation is called Cooperative Path Planning Using Responsibility Sensitive Safety Based Potential Field with Sigmoid Curve. And today I'm going to separate this presentation into 5 parts. First, I will give an introduction about autonomous driving and research motivation, and then I will introduce to what it is potential field in autonomous vehicle, and then I will present the so-called responsibility sensitive safety model combined with potential field with sigmoid curve, and then I will show the corresponding simulation results and results and some analysis. And then I will end it with a short summary. So in the past few years, the traffic accidents are increasing. And according to this table, we can see the number of the injuries are increasing into the 6 million in 2019, and most of the responsibility was taken by the drivers. So therefore, the autonomous vehicles become a key technique to achieve the so-called safe driving. And I want to introduce some components or concepts of the current autonomous vehicles. So as we know, the whole system, the whole autonomous driving system can be divided into perception, planning, and control. So as my presentation focuses on the planning module, so especially with the path planning, so I'm going to introduce the concepts of global path planning and the local path planning. So the global path planning is usually defined pure geometric path planning from starting point to target point. And the local path planning is collision avoidance path planning, actually based on the real-time information collected by onboard sensors. But however, road tests of the several autonomous vehicles are caused serious traffic accidents. So back to the 2018, the autonomous Uber SUV struck and killed a pedestrian. Sensors cannot detect her 6 seconds before he recognized this woman. And in the 2020, the Tesla Model 3 with some autopilot mode and didn't see the truck, and the safety feature didn't stop the collision. And so far, there have been 465 autonomous vehicle collision reports, according to the Department of Motor Vehicles, Government of California. So 3 main causes were concluded. The first one is a sensor failure. So sensors cannot detect or estimate accurately among surrounding objects. And the second is planning paralysis. So AVs couldn't plan a collision-free trajectory in traffic emergencies. And the last one is no cooperation. So current AV was not able to collaborate with other road users. So therefore, our proposal provides a specific method to enhance the safety features of AVs in terms of path planning by using the vehicle-to-vehicle communication. And in this slide, I would like to introduce what it is potential field. And this method is actually a famous local path planning method used in robotics, and it is inspired from the classical mechanics. So that's imagined in an electric field. There are two components. We name the target point and robot. We put the negative component in the target point and positive component around the robot. So the robot will, of course, move to the target point, and the potential field is can imitate this kind of mechanism. And let's consider about the thing that there have two obstacles here, and we put the same positive components around these two obstacles. So by applying this method, the robot can arrive at the target point while avoiding these two obstacles. So the PF can imitate this kind of process. And in this slide, I can introduce how we apply the PF in autonomous driving. So usually the PF is able to model the 3D risk model from the giving information about the surrounding environment. So first we actually start the PF, and then he will model the 3D PF of the road boundaries and road center line, and of course the front obstacle vehicle. And by summary these two potential fields, we can get this so-called total potential field, and then we just directly apply the gradient descent method to find the local path. So you can see here the path from the start point to the target point. However, there have several inherent limitations existed in PF that is pointed out by these references. So there are four inherent limitations actually. So the first one is a trap situation, and then no passage between closely spaced obstacles, and oscillations in the presence of obstacles and oscillations in narrow passages. So there has a lattice method proposed to solve the above limitations. So the proposals are like they use a sigmoid curve to combine with PF as a hybrid path planning, and then the PF is combined with a two-dimensional joint probability density to estimate the collision risk from the surrounding environment. And also they are capable to find the shortest path while considering the riding comfort. But we have those concerns below. The first one is safety features were not considered or emphasized in this reference, and the computational cost was further increased. And the last one is cooperative driving was not discussed. So in this slide, I'm going to introduce the responsibility sensitive safety model that is proposed by the Intel Mobileye company. So let's watch this video first.
Everyone agrees that autonomous vehicles are the future of mobility. But how can we be assured of their safety? Although we don't consciously think about it, humans follow a few basic principles to help us drive safely. For example, always maintain a sufficient distance from the vehicle ahead of you, or the right-of-way is given and not taken. However, these principles are subjective and open to interpretation. To provide true safety assurance for autonomous vehicle decision-making, we must first clearly define those principles. Only then will we be able to program an autonomous vehicle that will be smart enough to negotiate the road alongside unpredictable human drivers. In order to formalize human common sense, Mobileye has developed the responsibility-sensitive safety model. RSS is an open and transparent model that uses mathematical formulas for safe decision-making by defining what constitutes a dangerous situation, what caused it, and the proper response to the dangerous situation. By doing so, we can ensure that the autonomous vehicle will not initiate a dangerous situation and also ensure that it responds appropriately when a dangerous situation is forced upon it by others. For example, while merging into traffic, the autonomous vehicles will cut in only with a minimal safe distance as defined by RSS. RSS builds upon these simple definitions of a dangerous situation by incorporating more complicated scenarios, such as junctions, limited sensing scenarios, and even unstructured roads. This allows us to gain full coverage of all possible scenarios in a multi-agent environment and clarify responsibility for collisions involving automated vehicles in the real world. These are just a few examples of how RSS is designed to mimic human judgment using mathematical definitions. At Mobileye, we believe that the challenge of providing verifiable safety assurance of automated vehicles is one the entire ecosystem must solve together. Therefore, we invite industry players and regulators to engage with RSS as a starting point for finding a true safety guarantee for autonomous vehicles. Join us in our journey to make safe autonomous driving a reality. Mobileye.
So the RSS model is actually based on these 5 common sense rules. The first is to not hit someone from behind, and the second is to not cut in recklessly, and the right of way is given, not taken. And be careful of areas with limited visibility. And if you can avoid an accident without causing another one, you must do it. So based on this kind of model, we combine it with the potential field. So we apply the longitudinal RSS and the lateral RSS inside of the potential field. So here is the longitudinal RSS formulation. The details are explained in the paper. So if you are interested, you can refer to the paper. And the next is how we calculate the sigmoid curve. So first is about the central point. K is mean slope here. So we actually can calculate this slope of the sigmoid curve by using this formula. And this formula considers about the longitudinal RSS and the relative distance between the eagle vehicle and the front obstacle vehicle. And also we put a K con here. It means the slope constraint that consider about the vehicle dynamics. And then we consider 2 circumstances in a straight highway. So the first one is overtaking scenario. So we consider it safe to overtake multiple obstacles when the longitudinal RSS is less than half of the relative distance between obstacles. So in this scenario, the proper deceleration is required for overtaking manual. And the next is a platoon scenario. So you can see there is a 3 vehicle platoon driving at the upper lane, and there is 1 dynamic obstacle driving at the lower lane. So in this situation, when the dynamic obstacle 2 performs a suddenly decelerating action without pre-warning, and the eagle vehicle is able to send a cooperative velocity to a platoon via V2V communication. So the platoon is able to receive that requirement and perform the cooperation. And in this slide, I can show some simulation studies and analysis results. So I actually give the 3 path burners here. The first is proposed one, and the second is the lattice hybrid method from the reference. And the third one is we only use the PF best path planning method. So you can see here scenario 1 is 2 stated obstacles are closely spaced. And we can observe that the proposed one can plan a more comfortable path. And the computational time is also similar to the PF-only method. And the proper deceleration and cooperative speed of velocity is calculated by the CHPP method. And then the next is the scenario 2, and we actually just simulate a 3 vehicle platoon in here in the upper lane, and the dynamic obstacle at the lower lane will suddenly decelerate without the pre-warning. So you can see also the computational time is similar to the PF-only method, and the vehicle platoon is able to cooperate with the given speed. And here we come to the conclusion. So in today's presentation, I introduced the research introduction and motivation, and I also introduced the current PF applied in AVs and how it combined with responsibility sensitive safety model and the Sigmoid curve. And I also evaluate it in MATLAB Simulink. So future work will focus on the surrounding vehicles, intention awareness, and study more challenge scenarios like intersections, curve road, etc. So thank you very much.